Fitzroy. I'm the CEO and President of Giyani Metal Corp, and I'm here in Johannesburg at our demonstration plant with some key members of our team. Justin is our Group Process Engineer, and Desiree is our Lead Process Engineer. And this is Liani from Minipex, we're a plant operations group who operate 46 plants in the EMEA region. So we're very lucky to have them partnering with us and on board. And there's lots to talk about today, so let's move on to it. Behind us, you'll see 100 tons of ore, which is taken from our Hill asset in Botswana. And this is where all the ore is going to be sourced for our demonstration plant and our commercial facility, which will be in Botswana as well. So Justin, once we have the ore here, what happens to it after that?
Charlie, it's a fairly standard hydrometallurgical process which we've adapted to the specific requirements of the manganese product that we're trying to produce, which is obviously key criteria there being that the fact that it is a high purity level, 99.95% or better, which is a critical matter for feeding that into the battery production system, so that the quality of the batteries that are produced is not affected by contaminants that come in with the precursors. So basically from the ore that we have here, from our quite unique Hill deposit, a very high quality ore, the system is then fed, so our initial feed comes in from the bagging tower. So much of the equipment on this skid is now new. So you may recognise from last time the parts of the tower were available. This has now been fully assembled. We've also got the mill and the screen. We've got our mill water recirculation system. So that's a critical part of the Botswana stuff, is preserving water. So we don't just have a single pass through on the mill water circuit. We actually have the full system recirculating water so that we don't waste it.
You've also been doing some optimization work.
We have.
And there's some chemicals and things which have been removed.
We've developed a new process which we've been able to apply here. Which has allowed us to remove one of the reagent systems, which was the use of hydrofluoric acid to remove calcium and magnesium. So we found a different way to decontaminate or purify the system of calcium and magnesium, which allowed us not to use the HF, which is fantastic. Now we don't have hydrofluoric acid on site. Hydrofluoric acid is a dangerous and unpleasant chemical. It requires a lot of safety engineering around it. So the fact that we've been able to remove that means that there's a lot less basically dangerous chemicals on site that we now don't have to worry about, don't have to engineer around. We don't have any issues with it. So basically this is the leach circuit, and that's typically the first stage that you have. So after milling in any of the hydromet circuits that are running on run-of-mine, you basically mill to get a particle size that you require to optimize the dissolution of your target metal. On a gold plant, that would typically be somewhere in the region of 75 microns. Again, we've got this highly beneficial, highly favorable ore of ours. We're only grinding to about 150 to 220 micron. It's a relatively coarse grind. So the benefit of that, A, it's lower energy input to get to the slightly larger particle sizes, and B, the slightly more coarse material filters better. It's easier to pump, it's easier to handle, and the whole process is just a lot simpler with a slightly more coarse particle size than a typical gold plant.
The leaching is relatively straightforward. We remove some harmful chemicals which are very beneficial for our process, and the leach that comes out is already quite clean.
It is.
So we're now talking about not major impurity removal, it's just to get that high purity product
exactly.
Which we need.
So we're removing parts per million of impurities.
Right.
So we've got a clean leach. We have to remove a small amount of impurities so that we can get onto target for the crystallization.
Exactly, this is getting all towards getting that target spec for our off-takers and groups which need certain requirements for their battery precursor materials, and that's really where we're pushing this. So let's move on to the next bit. Great, so we're here at the next phase of the leach impurity section. You can see these vessels behind us. Desiree is going to give us a bit more background on what's going on.
Yes, so these are stainless steel reactor vessels. So they will all feed to each other with gravity feed. And we'll have these reactor vessels will be run at a set point controlled temperature that we'll control with these heater jacketed that we have around the reactor vessels. We'll inject steam on this side and the condensate will come out at the bottom. And this will all be controlled and automated process.
So the automation there is handled by DCS, which is a distributed control system. So we've supplied that by Yokogawa. It's an absolute world-class system. So the DCS allows us to maintain steady state across the plant. So if we were trying to do that with humans, you can. You probably have 20 times as many personnel in here, which has its own risks associated with it. 20 times as many people, it's cluttered, there's no space, that kind of stuff. So we don't want that number of people on the site. So what you do then is you use a DCS. The DCS controls all of the aspects of the process. It will control flow, it will control pH, it will control temperatures, controls reagent additions, it controls agitation speeds so that we can do R&D against agitation power and understand and optimize the main process. And the key thing there is that you have steady state so that when you make a change, you understand the difference. So if your plant is being operated manually or being operated by a sort of primitive control system, it might be fluctuating inherently. And you never really know, well, I made a change, but was that now, the change that resulted from that, was that now an inherent fluctuation, or is that something that responded? So the great thing with this is we have a steady state.
Part of our purification process is where we precipitate all of our impurities out of solution, which is our manganese-rich solution, and then we filter them out. On top here you can see all of our filter presses for the different purification steps that we take. So we filter them, the solids fall down from the bottom, which will then be removed and go to the tailings facility.
So what we're doing with the tailings here is we're taking them to a place called Holfontein, which is a industrial waste disposal facility. So it's a highly professional, thoroughly certified and checked and in accordance with all the legislative requirements around that. So all of our material, including our liquid waste and liquid effluent from the facility, will go to Holfontein. On the main plant, obviously, we will have a tailings dam that will handle all of this material. And we're looking at opportunities where that material can be slightly modified, slightly optimized, and potentially produce useful material that could actually go into other industries. So the effluent on the main plant will not go to waste. It will go through a water treatment plant and be brought back in so that we're not wasting water as a matter of principle. We just don't do that, right?
It really makes me very proud to work for a plant and a company that really reduces and minimizes effluent.
So we put the control room operators who are amongst the highest skill and most involved persons on the project. So they will be in the container, which is equipped with windows, as you can see. All of the sampling that we do, and that's 27,000 samples a month, go into our laboratory facility.
And a quick turnaround from the lab will also make commissioning fairly simple to make quick decisions.
So to recap, the ore is taken, put in the hopper, is ground, is leached, and then impurity removal. And then we've got to this stage now, which is, as you said, the heart of the process. And so what happens here?
The crystallization, heart of the process. So the crystallizer system performs a number of functions. A, as you'd guess by the name, it produces crystals, which are the end product. So it's a dry material, easy to ship, so that we can send that across to Europe, the United States. But what the crystallization also does, it's an additional and final impurity removal. So because you have a differential profile of crystallization in the unit, we're able to get the manganese out on its own, and residual impurities either don't crystallize or crystallize at different rates, and then they don't basically enter into that crystal matrix. Now the primary crystal that we form, which is formed in the main crystallizer outside, basically we have a two-stage crystallization at the moment. So the crystals that are produced in the crude crystallizer drop into this tank here, where they're re-slurried with demineralized water, which we produce in-house over there. And the demineralized water then has a far, far lower impurity profile than the original feed liquor had. So what you do is you have a preferential removal of manganese with a small amount of impurities dissolved into demon water, which basically gives you that same manganese and a tiny impurity profile. That then goes into the pure crystallizer, and the pure crystallizer repeats the process, but there you get your 99.95, 99.96% purity product that's coming out in crystal form because you had a much lower profile of everything else against the manganese to start with.
This is what separates us and shows that our product is that high purity, that next step. It enables us to get that real high purity, which is the key thing the off-takers are looking for, OEMs looking for their batteries.
This is our dryer. So our product obviously comes off through a filtration process. The washed crystals with that residual moisture are drawn into this system, and the system basically just removes the moisture.
Fantastic.
Our product dryer will reduce our moisture content from 15% to about 2%.
Wow.
Easy handling.
So Justin, we're outside now at the crystallizers, which are the smallest commercial crystallizers we could get.
This facility is just a scaled down version of what will go into Botswana. Every pump, every valve, every instrument that you see here will exist on the main plant. The main plant will operate exactly like this one does. All the learnings coming from here translate directly to the main plant. So these 4 tanks that you see in front of you here, this is our effluent storage tanks. So the effluent, liquid effluent, aqueous effluent that we produce here will be collected by truck and also goes to the Holfontein facility that we were referencing with the solids. So it's all disposed of very responsibly, traceably, in a registered and well-controlled facility. which is obviously key to everything that we do.
Whilst we are producing a high-spec, consistent, steady-state product, it's also that ability to test. And this enables us to do optimization test work whilst we're doing our DFS, which enables us to optimize the DFS, reduce OPEX ahead of it, ensure we're reducing reagent consumption and reducing carbon. So all these things are building in. It really is a fantastic facility.
Yes, and show how we can reuse and reduce and really do it in an environmentally friendly way.
Yeah. Thank you for updating on the progress and showing us around the plant and explaining a bit more. This facility is just phenomenal. You have to come and see it.
Absolutely.